This is the first of a new series of videos that I'll be making about reaction rate theory and rare events methods. This is a course that I'm teaching at UCSB in the spring of 2016, and it's a course that I've been very excited about teaching for a long time. And I want in this course to really move away from the traditional focus on reactor engineering and catalysis. Now, with that said, many of the first lectures will be about those kinds of topics, a sort of review of the first graduate course in reactor engineering and catalysis that we have here in the graduate program. But also, I think that these topics are so closely identified with kinetics in the field of engineering, and that sometimes that's kind of unfortunate, right? So I have colleagues who work on things like systems biology, electrochemistry, drug delivery, nanoparticle synthesis, nucleation, biophysics, SFA, where you have things jumping in and out, with some lifetime, and then there's crystal growth processes, there's polymerization processes. In fact, both of those are shown in the one diagram over here at the right. That's a titanium chloride crystal, and you can see the spiral growth patterns on its surface, and on the edges of those spiral terraces you see little clumps of polyethylene growing, right? So I have a colleague who Susanna Scott, who works in olefin polymerization, and another colleague that I collaborate with who works in the area of crystal growth. And this one figure kind of captures both of those things, so I like it a lot. There's also, of course, a lot of solid state mobility problems. Solid state diffusion and defect migration are problems that involve rare events, so material science should care about those quite a bit. And of course, there's photochemistry applications. Now, so these are the sorts of things that are happening in chemical engineering departments around the country, in areas where I think that the kinds of material that we'll cover in this course should, in principle, be broadly useful. I think that as you look beyond engineering, you find that there's also somewhat compartmentalized views of this subject in chemistry and physics. And I think that that was famously noted by Hanji Talkner and Borkovec in 1990 in their review article, where they point out that if you check out a chemistry book from the Library on Kinetics, you'll find that it really scarcely makes mention of the important results from Kramers. And if you check out a non-equilibrium stat-mech book, on rare events, for example, you'll find that often they don't even mention transition state theory. And so these things are quite important omissions, and I think that they're areas where the literature is somewhat in need of a book that bridges these two different disciplines, and that's one that I'm working on as we speak. So let me go ahead and really emphasize some of the topics that we'll cover in the lectures that I'm going to be uploading this quarter. These include things like chemical equilibrium, things like free energy surfaces, also things like stochastic processes, Kramers and Grody-Hines theory, methods like transition path sampling and non-adiabatic chemical reactions, techniques for computing transition state theory rate constants and for correcting them with reactive flux and tunneling corrections. We'll talk about diffusion controlled rates. We'll talk about unimolecular reactions, and we'll talk about the important phenomenological models of kinetics and catalysis, and we'll also talk about things like collision theory. So this is sort of a sample of the kinds of things that we'll be talking about in the course, and what I want to drive home is this point that the literature in the fields of engineering, chemistry, and physics really does have almost no overlap. So these are three classic books drawn from each of those different areas. In engineering, there are the books by Michel Boudard, and if you look at those, they pretty much cover chemical equilibrium, phenomenological models of kinetics and catalysis, free energy relationships, potential energy surfaces, and transition state theory. And then as you move over into the chemistry discipline, there's a little bit of overlap between those two, but for the most part, there's very little overlap between the things that the chemists talk about in their classic books, Steinfeld, Haas, and Francisco. So this is diffusion control, unimolecular reactions, transition state theory, and then phenomenological models as well. Then if you go over into the condensed matter dynamics work from the physics community, for example, by Abraham Nitzan, has a beautiful book as well, you see that he does a very nice job talking about stochastic processes and Kramers theory and non-adiabatic reactions, and then it starts to get pretty thin when you talk about transition state theory. So there's really very, very little overlap in these areas, even when you look at the most authoritative books in the different subjects. And so in this course, I think one of the things that makes this course and the book that I'm working on quite unusual is that we'll be talking about all of these different things. So the first thing that I want to address in the course is, what is a reaction rate? So probably from a chemical engineer's perspective, they would give you something that talks about conversion versus time. From a chemistry perspective, they might tell you it's the derivative of the concentration versus time. And in fact, those are both rather narrow definitions. You don't have to have any time dependence. And in fact, we design reactors all the time that operate at steady state, for example, and we know that reactions are happening in them. And so the reaction rate itself doesn't have to necessarily be identified as a concentration derivative as a function of time. Instead, we should think of the reaction rate as a property of the mixture. Much like a diffusivity or thermal conductivity or viscosity, it depends on the composition of the mixture and on the temperature. And formally, it is a Poisson parameter that tells you about the expected number of events per domain per time. And so that's a perspective that we will adopt quite often in the course, thinking about reaction rates as Poisson parameters and thinking about these things as stochastic processes. So it's important to realize that the nature of that domain determines a lot about the units of the reaction rate and the way it enters mass balances, right? So this is the sort of general equation that would involve a reaction rate. You have the accumulation, the flow in and flow out terms, and then you have the degeneration terms sitting here, right? So this is where the reaction rate enters this species balance equation. And in fact, you can take this species balance equation and cross off the appropriate terms, integrate over the appropriate volume, and get each of these different reactor design equations for the classic chemical engineering reactor types. Now, if I return just for a moment and point out that this is a bulk chemical reaction rate, this is something that would have a rate of moles of reaction per volume per time, for example, sitting here in this balance equation. But in fact, reactions can take very different kinds of forms. For example, surface reactions can be moles of reaction per area per time, and you can have reactions at a specific site where you have reaction events per site per time, and we usually talk about those in terms of turnover frequencies. So I think that that's where I will stop for this very short lecture that just really introduces the course syllabus and the topics, and also defines the reaction rate.